Hey there, how's it going? Thanks for joining me today. Whether you're relaxing at home, on your commute, or winding down for the evening, I'm really glad you're here. Because today, I want to tell you about a phone call that changed everything. Not just for one person, not just for one country, but for every single human being on this planet. And it all started at 3:17 a.m. Pacific time, on what seemed like just another ordinary Tuesday. Picture this. You're Maria Gutierrez, a 26-year-old graduate student at the University of Arizona. You've been up since midnight running routine observations at the Catalina Sky Survey, which sounds incredibly important, but honestly, most nights it's about as exciting as watching paint dry. You're looking for asteroids, space rocks that might pose a threat to Earth. 99.9% of the time, you find absolutely nothing dangerous. The other 0.1%? Well, that's where our story begins. Maria's sitting in front of 3 computer monitors in a room that smells like coffee and the faint ozone scent of electronic equipment. Outside, Tucson is fast asleep. Inside, she's doing what she's done hundreds of times before, comparing images of the same patch of sky taken 20 minutes apart. Most of the time, the images are identical. Stars don't move in 20 minutes. Galaxies don't shift, but asteroids do. At 3:17 a.m., Maria sees something that makes her blood run cold. There's a dot, a faint, unremarkable dot that wasn't in the first image but appears in the second. That's not unusual. The Catalina Sky Survey finds about 3 new asteroids every single night, but this dot is moving in a way that sends ice through her veins. It's not following a nice, safe orbit in the asteroid belt between Mars and Jupiter where it belongs. This thing is moving in a trajectory that brings it uncomfortably close to a very specific blue planet. Our planet. Maria's hands start shaking as she runs the preliminary calculations. She double-checks them, triple-checks them, runs them through a different program. The numbers don't change. They keep giving her the same terrifying answer. Now, I want you to imagine what's going through her head right now. 6 years of graduate school, 3 years working at Catalina, and she's found hundreds of asteroids. But this one is different. This one is roughly 300 meters across, about the size of the Eiffel Tower, and according to her calculations, it's not just going to come close to Earth, it's going to hit us. The impact probability? 97%. Time until impact? 14 months. Here's the thing about finding a civilization-ending asteroid. There's a protocol, a very specific, very serious protocol. First, you check your work until your eyes bleed. Then, you call your supervisor. Then your supervisor calls their supervisor. Then things get very, very official very quickly. Maria's first call goes to Dr. Robert Chen, the Catalina Sky Survey director. It's 3:28 a.m., and Chen's phone buzzes him awake in his bedroom 12 miles away. When he sees Catalina Sky Survey on his caller ID at 3:30 in the morning, his stomach drops. In 15 years of running the program, he's gotten exactly 4 calls at this hour. 3 of them were false alarms. One of them led to a year-long monitoring program for an asteroid that ultimately missed Earth by 6 million miles. Maria? Chen's voice is thick with sleep. Please tell me this is about equipment failure. Dr. Chen, I need you to look at observation CS25-0417 immediately. I've run the calculations 6 different ways. This is not a drill. The line goes quiet for so long that Maria wonders if the call dropped. Finally, Chen speaks, and his voice has changed completely. I'll be there in 20 minutes. Don't call anyone else yet. And Maria? Save everything. Every calculation, every image, every keystroke. Everything. 23 minutes later, Chen burst through the observation room door, his hair sticking up at odd angles, wearing yesterday's shirt and tomorrow's worried expression. Maria hands him the data without a word. For the next 47 minutes, they work in complete silence, running calculations on 3 different computer systems. At 4:38 a.m., Chen makes the phone call that starts the cascade. He dials a number that connects him to the Planetary Defense Coordination Office at NASA headquarters in Washington, D.C. It's 7:38 a.m. on the East Coast, but the PDCO operates around the clock for exactly this reason. The phone rings twice. PDCO, this is Johnson. Johnson, this is Robert Chen at Catalina Sky Survey. We have a potential impact event. Preliminary calculations show 97% probability, 14-month timeline. There's a pause that lasts exactly 4 seconds. Johnson is checking Chen's credentials on his computer screen. Doctor, Chen, I need you to transmit all data immediately. We're going to conference in ESA, JAXA and Roscosmos. How confident are you in these numbers? Chen looks at Maria, who's been running calculations for over an hour. She nods grimly. Johnson, I've been doing this for 15 years. I've never been more certain of anything in my life. We have 14 months to figure out how to save the world. Within 6 hours, observatories across 5 continents have their telescopes pointed at the same patch of sky. The Arecibo Observatory in Puerto Rico, IFS. Well, what's left of it after the collapse, but its replacement systems are online. The Very Large Telescope Array in Chile, the Subaru Telescope in Hawaii, radio telescopes in Australia. Even the Hubble Space Telescope is redirected from studying distant galaxies to focus on this 300-meter piece of rock that's about to become the most important object in the solar system. By 10 a.m. Pacific time, the confirmations start rolling in. ESA confirms the trajectory. Impact probability, 96.8%. JAXA confirms the size estimate. 300 meters diameter, roughly spherical. The Russian Academy of Sciences confirms the composition analysis. It's a stony asteroid, what scientists call an S-type. Dense, solid, and moving at 25 kilometers per second relative to Earth. By noon, the preliminary impact zone calculations are complete. The asteroid, now designated 2025 DX41 TR, will hit somewhere along a 3,000-kilometer track stretching from the Pacific Ocean through California and Nevada. Best-case scenario, it hits water off the coast, creating tsunamis that devastate everything from Alaska to Chile. Worst-case scenario, direct impact on Los Angeles or San Francisco. But here's what's really wild about this whole situation. 12 hours ago, this asteroid didn't exist in human consciousness. It was just another piece of rock following the same orbit it's been on for 4.5 billion years. Now, suddenly, it's the most famous rock in the solar system. TV networks are scrambling to find asteroid experts who can explain what's happening. The White House Situation Room is being prepped for an emergency briefing. The UN Secretary General is being woken up in New York, and it all started because a graduate student noticed a dot that moved. Think about that for a second. Everything that's about to unfold, the global response, the technological miracles, the international cooperation, the potential evacuation of the entire West Coast, ESPET, it all traces back to Maria Gutierrez, squinting at computer screens at 3:17 in the morning, doing the job she's done hundreds of times before. But this time was different. The cascade of phone calls continues throughout the day. The NASA administrator calls the President's science advisor. The President's science advisor calls the Secretary of Defense. The Secretary of Defense calls the President, who's having breakfast with the Secretary of State when his secure phone rings. Mr. President, we have a situation. By 6 p.m. Eastern Time, the President is in the Situation Room with advisors who look like they haven't slept in days, even though this crisis is barely 15 hours old. On the main screen is a computer simulation showing Earth's orbit and a red line that intersects it at exactly the wrong place and time. So, The president says, loosening his tie. How do we stop it? The room falls silent. Because here's the thing, nobody wants to say out loud. We've never actually had to stop an asteroid before. Sure, we've run simulations, we've planned missions. NASA even crashed a spacecraft into an asteroid in 2022 to test the concept. But that was practice. This is the real thing. Dr. Sarah Martinez, the NASA administrator, clears her throat. Mr. President, we have options, but we need to act fast. Every day we wait makes those options less effective. How much less effective? At 14 months out, we need to change the asteroid's velocity by about 2 centimeters per second, roughly the speed of a crawling snail. Wait until 3 months before impact, and we'd need to achieve 100 times that change. Wait until 1 month before impact, and... She pauses. Well, we'd be looking at evacuation rather than deflection. The president leans back in his chair. Through the reinforced windows of the Situation Room, Washington, D.C. continues its normal evening routine. People are heading home from work, making dinner plans, worrying about mortgage payments and parent-teacher conferences. None of them know that in a room beneath the White House, a small group of people is discussing how to prevent the end of civilization as we know it. What do you need? The president asks. Everything, Martinez replies. Every rocket, every space agency, every ally. This isn't an American problem, Mr. President. This is a human problem. And that's when the real work begins. Within hours, secure communication channels light up between Washington, Moscow, Beijing, Brussels, Tokyo, and New Delhi. For the first time in modern history, the world's space agencies aren't competitors, they're teammates. Because when you're facing extinction, nationality becomes irrelevant. The European Space Agency offers their Ariane rockets. SpaceX volunteers their Falcon Heavy fleet. Blue Origin opens their manufacturing facilities. The Russians dust off plans for nuclear-powered spacecraft they've been developing in secret. The Chinese reveal ion drive technology that's years ahead of anything the West thought they had. India offers their precision manufacturing and mission control expertise. By midnight, exactly 21 hours after Maria first spotted that moving dot, humanity has a plan. It's ambitious, risky, and absolutely necessary. 8 kinetic impactors launched on different trajectories, calculated to hit the asteroid from multiple angles and nudge it just enough to miss Earth. The margin for error, 0. But here's what gives me chills about this whole story. The speed. 21 hours from discovery to global mobilization. 21 hours from, hey, there's something weird in these images, to, we're going to launch 8 spacecraft to punch an asteroid. When humanity is truly threatened, we can move mountains. Or in this case, we can move an asteroid. The news breaks at 6 a.m. Pacific time the next day. Maria Gutierrez is still at her desk. She hasn't gone home yet, when every major news website in the world simultaneously crashes from traffic overload. CNN, BBC, Reuters, Associated Press, Geo, they all lead with the same headline in a dozen different languages. Asteroid on collision course with Earth. Social media explodes. Asteroid becomes the top trending topic in every country with internet access. Bruce Willis jokes flood Twitter for exactly 6 hours before the gravity of the situation silences them. Stock markets open with the biggest single-day drop in history, then recover by noon as investors realize there's no point in selling if money might not matter in 14 months. Religious movements surge overnight. Some preach end times, others organize relief efforts. Gun sales spike 5,000% in the United States. Marriage proposals increase by 3,000% worldwide. Apparently, the prospect of cosmic annihilation makes people want to either prepare for war or declare their love. Sometimes both. But something else happens too, something that gives me hope about our species. Neighbors start talking to neighbors they've ignored for years. Families plan reunions. People volunteer for disaster relief training. Online forums dedicated to asteroid science, AIP, which had maybe a few thousand members before, suddenly have millions of people sharing calculations and asking questions about orbital mechanics. Humanity doesn't just panic in the face of extinction. We also come together, and in a small observation room in Arizona, Maria Gutierrez finally goes home at sunset, 24 hours after arriving for what she thought would be a routine night shift. Her boyfriend asks how her day was. She looks at him and starts laughing. Not because anything is funny, but because what else do you do when you've just become the person who discovered that the world might end? It was interesting, she says. We should probably call your parents. Outside, the sun sets on a world that will never be the same. Because now we know. In 14 months, something the size of the Eiffel Tower is going to arrive from the depths of space. And everything that happens next depends on whether 8 pieces of human technology can hit a moving target 400 million kilometers away. No pressure at all. Now that we've lived through those terrifying first 24 hours, I think it's time we got to know our cosmic visitor a little better. Because here's the thing. To understand what's heading our way, we need to understand what asteroids actually are. And trust me, the truth is far stranger than just flying space rocks. Let me take you on a journey. Picture the solar system 4.5 billion years ago. Earth, sir. That's 4,500 million years. A span of time so vast that if Earth's entire history was compressed into a single day, humans would appear in the last few seconds before midnight. Back then, our solar system looked nothing like the orderly, stable place we know today. Instead of planets orbiting peacefully around the sun, there was chaos. Pure, beautiful, violent chaos. Imagine a massive disk of dust and gas, stretching billions of kilometers, swirling around our infant sun like the universe's most spectacular cosmic hurricane. In this swirling disk, something magical was happening. Tiny specks of material, grains of dust smaller than the period at the end of this sentence, were sticking together. Think about the last time you walked through a spider web and couldn't get all the silk off your jacket. Now imagine that happening in space. But instead of spider silk, it's gravity and electrostatic forces. And instead of your jacket, it's chunks of rock and ice. These specks grew into pebbles. Pebbles crashed into each other and stuck together to become boulders. Boulders slammed into other boulders and became mountains. Mountains collided with mountains and became something we'd barely recognize as the building blocks of planets. It was like the universe's most violent game of cosmic snowball fighting, where every snowball that hit made both participants bigger and more dangerous. Most of this material eventually clumped together into the planets we know today. Mercury, Venus, Earth, Mars, COZ, they're all the winners of this 4 billion year demolition derby. The survivors that managed to sweep up everything else in their orbital. Neighborhoods. But between Mars and Jupiter, something went wrong. Actually, let me rephrase that. Something went very, very right for Jupiter, and very, very wrong for everything else. Jupiter is a monster. I don't think we really appreciate this from our comfortable perch here on Earth, but Jupiter is so massive that it contains more material than all the other planets combined. It's so big that it doesn't really orbit the Sun, ISA. Both Jupiter and the Sun orbit around a point that's just outside the Sun's surface. Jupiter is less a planet and more like a failed star, a cosmic vacuum cleaner that's been sucking up everything in its vicinity for 4.5 billion years. And here's where our asteroid story really begins. In the region between Mars and Jupiter, chunks of rock and ice were trying to do what chunks of rock and ice had done everywhere else in the solar system, stick together and form a planet. But Jupiter's massive gravity kept stirring the pot. Every time these building blocks got close to forming something planet-sized, Jupiter's gravitational influence would speed them up, slow them down, or send them careening into each other at such high velocities that instead of sticking together, they shattered. So, instead of a planet, we got millions of fragments suspended in an eternal construction site, the asteroid belt. It's like a cosmic junkyard filled with the leftover pieces of a planet that never quite made it. Some of these fragments are tiny, grain of sand sized. Others are massive. Ceres, the largest asteroid, is 900 kilometers across and contains about 1/3 of the asteroid belt's total mass. But here's where it gets really fascinating, and why our incoming visitor is more than just a big rock. Not all asteroids are created equal. They're like cosmic archaeological samples, each one telling a different story about the early solar system. Take the C-type asteroids. The C stands for carbonaceous. These make up about 75% of all known asteroids, and they're dark as coal. When I say dark, I mean they reflect less light than charcoal. If you painted your car with C-type asteroid material, it would be nearly invisible at night. But these dark, unremarkable-looking rocks are actually time capsules containing the same carbon-rich material that brought water and organic molecules to early Earth. Think about that for a second. These asteroids aren't just space debris, they're delivery trucks that may have brought the ingredients for life itself to our planet. Every drop of water you've ever drunk, every carbon atom in your body, might have arrived here 4 billion years ago, aboard asteroids exactly like the C-types we see today. Then there are the S-types. S for stony. They make up about 17% of known asteroids, and they're the show-offs of the asteroid belt. They're made of silicate rock mixed with metallic iron and nickel, and they actually glow brighter than the C-types, making them easier for our telescopes to spot. But don't let their good looks fool you. These are the asteroids that have left the biggest scars on Earth. Remember Meteor Crater in Arizona? That perfectly preserved bowl in the desert that's over 1 kilometer across and nearly 200 meters deep. That was created 50,000 years ago by an S-type asteroid, maybe 50 meters across, smaller than a football field. It hit the ground with the force of a 20-megaton nuclear bomb. The impact was so violent that it vaporized most of the asteroid instantly, leaving behind only scattered fragments of space metal mixed with shocked quartz, a rock that's been compressed so violently that its crystal structure changed permanently. But the most intriguing asteroids are the M-types, the metallic monsters. These represent about 8% of known asteroids, and they're made of nearly pure iron and nickel. These aren't just big rocks. They're the exposed cores of shattered protoplanets, the metal hearts of worlds that almost were. Here's something that will blow your mind. There's an M-type asteroid called Psyche that's about 200 kilometers across and composed almost entirely of metal. If we could somehow bring all that iron and nickel back to Earth, it would be worth $10,000 quadrillion. That's more than the entire global economy times 100,000. Psyche contains enough metal to supply Earth's industrial needs for millions of years. Of course, if we actually tried to bring that much metal to Earth, it would crash every economy on the planet and probably cause more chaos than the asteroid impact we're trying to prevent. But the point is, these aren't just rocks floating in space. They're treasure troves of materials that are incredibly rare here on Earth but common out there. Now, let's talk about our specific cosmic visitor, 2025 DX41. Based on the spectroscopic analysis from telescopes around the world, it's an S-type asteroid. That means it's made primarily of silicate rock with a healthy dose of metallic iron and nickel. It's roughly 300 meters across. Imagine the Eiffel Tower, but instead of elegant iron latticework, it's a solid chunk of space rock moving at 25 kilometers per second. To put that speed in perspective, a bullet from a high-powered rifle moves at about 1 kilometer per second. Our asteroid is moving 25 times faster than that. At that velocity, it could travel from New York to Los Angeles in less than 3 minutes. When something that massive moving that fast hits something as relatively stationary as Earth, The results are, well, let's just say they're not good for anything living nearby. But here's what's really wild about 2025 DX41. It's probably been orbiting the Sun for 4.5 billion years, following roughly the same path over and over again. For context, that means this chunk of rock has been making its rounds since before the Earth had continents, before life existed anywhere on our planet, before the Moon had even finished forming. For 4.5 billion years, it's been minding its own business, following a predictable orbit that kept it safely away from Earth. But sometime in the recent past, and by recent, I mean within the last few million years, something nudged it. Maybe it had a close encounter with Jupiter that altered its trajectory slightly. Maybe it collided with another asteroid and the impact changed its course. Maybe the gentle pressure of sunlight over millions of years gradually pushed it into a new orbit. Whatever happened, 2025 DX41 is no longer following a safe path through the solar system. Instead, it's on what astronomers call an Earth-crossing orbit, meaning its path around the Sun intersects with our planet's orbit. Most of the time, that's not a problem. Space is so vast that two objects can have intersecting orbits and never actually meet. But sometimes, very rarely, the timing works out perfectly. The asteroid arrives at the intersection point at exactly the same time as Earth. And when that happens, you get what scientists call an impact event, and everyone else calls the end of the world as we know it. The thing is, impacts like this aren't rare in cosmic terms. They happen all the time throughout the solar system. The Moon's surface is absolutely covered with impact craters because the Moon has no atmosphere to burn up incoming asteroids and no geological processes to erase the scars. Mars has impact craters. Mercury has impact craters. Even Venus, with its thick atmosphere that should provide some protection, shows evidence of massive impacts. Earth gets hit too, more often than most people realize. But we're lucky. Our planet has a thick atmosphere that burns up most small asteroids before they reach the ground, an active geology that slowly erases the evidence of ancient impacts. Still, we've found over 190 confirmed impact craters on Earth, ranging from small bowl-shaped depressions to massive structures hundreds of kilometers across. The difference between all those past impacts and 2025 DX41 is simple. This time, we know it's coming. For 4.5 billion years, Earth has been playing cosmic roulette, with asteroids as the ball and our planet as one of the slots on the wheel. Most of the time, the ball lands elsewhere, but occasionally, very occasionally, our number comes up. The dinosaurs learned this lesson 66 million years ago. The Tunguska forest learned it in 1908, and in 14 months, unless we do something about it, it's our turn to learn it again. But here's what's different this time. We're not helpless. The dinosaurs had no warning, no technology, no way to fight back. They were just passengers on a planet when their number came up. We're different. We have telescopes to see threats coming. We have rockets to reach them. We have computers to calculate their paths and figure out how to change them. We have something no species in Earth's history has ever had before, the ability to punch back. Whether that's enough remains to be seen. But for the first time in the 4.5 billion year history of impacts in our solar system, the target isn't just going to sit there and take it. 2025 DX41 may have been orbiting the Sun since before life existed on Earth, but it's about to learn that life has gotten a lot more interesting since then, and that changes everything about how this story ends. Now that we understand what's heading our way, I think it's time we talked about what happens when objects like 2025 DX41 actually hit Earth. Because here's something that might surprise you. Our planet's surface tells a story written in circles, and every one of those circles represents a day when the sky fell down. We've found over 190 confirmed impact craters on Earth. Think about that number for a moment. 190 times in our planet's history, something from space has hit us hard enough to leave a permanent scar. And those are just the ones we can still see after millions or billions of years of erosion, weathering, and geological recycling. The actual number of impacts? It's almost certainly in the thousands, maybe tens of thousands. Earth has been playing cosmic target practice for 4.5 billion years, and the game isn't over yet. Let me take you back to the very beginning, to a time when impact events weren't rare catastrophes but daily occurrences. 4.5 billion years ago, during what geologists call the Late Heavy Bombardment, Earth wasn't the peaceful blue marble we know today. It was a hellscape that would make the surface of Venus look welcoming. Picture this. For 600 million years, 600 million years, asteroids and comets pounded our young planet so relentlessly that the surface repeatedly melted and reformed. We're not talking about one impact every few million years like we see today. We're talking about multiple major impacts every day. The sky was literally falling constantly. During the worst of it, impacts were so frequent that the entire surface of the Earth was molten. Not partially molten, not just the impact sites. The entire planet was a ball of liquid rock orbiting the sun. Any water that tried to condense on the surface immediately boiled away. The atmosphere was a toxic soup of vaporized rock and metal. If you could somehow time travel back to that period and observe Earth from space, it would look less like a planet and more like a glowing ember. This went on for 600 million years. To put that in perspective, complex life has only existed on Earth for about 600 million years. The Late Heavy Bombardment lasted as long as it took for life to evolve from single-celled organisms to every complex creature that exists today. But gradually, very gradually, the bombardment slowed down. The solar system was running out of ammunition as the larger chunks of debris were either swept up by planets or ejected into interstellar space. Earth's surface finally cooled enough for water to condense and stay liquid. The first oceans formed, and in those oceans, somehow, against all odds, life began. But the impacts didn't stop completely. They just became less frequent, less devastating, and more selective in their timing. Fast forward 4 billion years to 66 million years ago. Earth has transformed completely. The continents have formed and drifted to recognizable positions. The oceans are teeming with life. On land, massive reptiles dominate every ecosystem from the Arctic to Antarctica. Dinosaurs have ruled the planet for 165 million years, HEAT, longer than mammals have existed. It's a warm morning in what will someday be called the Yucatan Peninsula. The area is covered by a shallow, tropical sea. Ammonites spiral through the water like living nautilus shells. Plesiosaurs cruise the depths like marine dragons. On nearby landmasses, Tyrannosaurus rex stalks through forests, while Triceratops graze in herds that stretch to the horizon. None of them know that their world is about to end. At approximately 11:30 a.m. local time, something appears in the sky above the Yucatan. It's moving so fast that if you blinked, you'd miss it. A chunk of rock and metal, 10 kilometers across, 2 larger than Mount Everest, screaming through the atmosphere at 20 kilometers per second. Let me help you visualize this. 20 kilometers per second means this asteroid could travel from the surface of the Earth to the International Space Station in 20 seconds. It could cross the entire continental United States in 4 minutes. As it tears through the atmosphere, it's moving so fast that the air in front of it can't get out of the way fast enough. The air compresses and heats up until it glows brighter than the surface of the sun. For a few seconds, there are literally 2 suns in the sky above the Yucatan. Then, it hits. In less than 1 second, asteroid. Less time than it takes you to say the word asteroid. This 10-kilometer chunk of space rock punches through the shallow sea and the limestone bedrock beneath it, creating a hole 20 kilometers deep. 20 kilometers! That's deeper than commercial airliners fly. The impact releases energy equivalent to 100 million megatons of TNT. To put that in perspective, the most powerful nuclear weapon ever detonated, a Soviet Union's Tsar bomber, was 50 megatons. This impact was 2,000 times more powerful. It was like detonating every nuclear weapon on Earth simultaneously, then doing it again 1,999 more times. The explosion creates a fireball 100 kilometers across. Everything within 600 kilometers is instantly vaporized, instantly not burned, not destroyed, but converted directly from solid matter to plasma. The shock wave radiates outward at supersonic speed, flattening forests and triggering earthquakes that make the strongest tremors in recorded history feel like gentle vibrations. But that's just the beginning. The impact excavates so much material that it literally punches a hole through the Earth's crust. Molten rock from deep underground shoots into the sky like a volcanic eruption on steroids. Some of this material travels so high and so fast that it escapes Earth's gravity entirely and ends up orbiting the Sun as a permanent reminder of the day the dinosaurs died. The rest comes back down. Within hours, superheated debris begins raining back down across the entire planet. Not just near the impact site, everywhere. Chunks of molten rock fall from space like a global hailstorm of fire. Forests on every continent ignite simultaneously. The Amazon burns, the forests of Sopeia. North America burn, the forests of Asia burn. Every tree on Earth that's not already underwater is suddenly fuel for a planetary wildfire. The sky fills with ash and dust and smoke until the sun disappears completely. For months, Earth is shrouded in darkness, so complete that photosynthesis becomes impossible. Plants die. The animals that eat plants die. The animals that eat the animals that eat plants die. Within a year, 75% of all species on Earth are extinct. Among them, every dinosaur larger than a chicken. 165 million years of evolutionary success, wiped out by 10 kilometers of space rock traveling at the wrong speed in the wrong direction at the wrong time. But here's the part that should give us pause, the part that makes this story relevant to our current situation. The dinosaurs were the dominant species on Earth for 165 million years. They survived ice ages, volcanic eruptions, climate changes, and ecosystem disruptions that would have wiped out lesser creatures. They were successful in ways that most species can only dream of. Humans have been around for 300,000 years. 300,000. We've been civilized for maybe 10,000 years. We've had the technology to detect incoming asteroids for maybe 50 years. In cosmic terms, we're barely a blip. We're so new that if Earth's history was compressed into a single year, humans would appear at 11:59 p.m. on December 31st. The cosmos doesn't care about dominant species. It doesn't care about intelligence or technology or art or literature. It doesn't care that we've written symphonies and split atoms and walked on the moon. Asteroids don't discriminate between dinosaurs and humans, between T-Rex and Nobel Prize winners. To an asteroid, we're all just made of the same basic elements: carbon, oxygen, hydrogen, calcium, psi, and we're all equally fragile when something massive hits the planet at cosmic pi. Velocities. This is the uncomfortable truth that 2025 DX41 represents. For all our technology and intelligence, we're still subject to the same cosmic lottery that claimed the dinosaurs. The universe is vast and mostly empty, but it's also full of rocks moving at incredible speeds in random directions. Most of the time, those rocks miss us, but sometimes they don't. The Chicxulub impact 66 million years ago wasn't a freak occurrence. It was just Tuesday in the cosmic shooting gallery that is our solar system, and it will happen again. The only questions are when and whether we'll be ready. Since Chicxulub, Earth has taken plenty more hits. They've been smaller, thankfully, but they've left their marks. There's the Poppyguy crater in Siberia, created 35 million years ago by an asteroid that scattered diamonds across hundreds of square kilometers, diamonds created by the incredible pressures of impact. There's the Chesapeake Bay crater, hidden beneath Virginia and Maryland, created 35 million years ago by an asteroid that triggered massive tsunamis along the entire east coast of North America. More recently, and by recently, I mean 50,000 years ago, an asteroid maybe 50 meters across hit the desert in what's now Arizona. It wasn't anywhere near as large as the Chicxulub impactor, but it still created Meteor Crater, that perfect bowl in the desert that's over a kilometer across and nearly 200 meters deep. The impact was so violent that it scattered fragments of space metal for kilometers in every direction. If a similar asteroid hit today near a major city, the devastation would be unimaginable. And then there was Tunguska. On June 30th, 1908, at 7:14 a.m. local time, something exploded above the Podkamennaya Tunguska River in Siberia with the force of 1,000 Hiroshima bombs. The explosion flattened 2,000 square kilometers of forest, Knoll an area larger than Dole, London. Trees 40 kilometers from the blast point were knocked down like matchsticks, all pointing away from the explosion center like frozen screams. What caused the Tunguska event? Most likely a small asteroid, maybe 60 meters across, that exploded in the atmosphere before hitting the ground. It never even reached the surface, but the airburst was powerful enough to be detected by seismic stations across Europe and Asia. The atmospheric shock waves circled the Earth twice. For several nights after the explosion, the sky glowed so brightly across northern Europe that people could read newspapers by the light. Here's the terrifying part. If the Tunguska asteroid had arrived 4 hours later, Earth's rotation would have positioned Moscow directly beneath the explosion. If it had arrived 8 hours later, it would have been London. A 60-meter asteroid, smaller than a football field, came within hours of destroying one of Europe's major capitals in 1908. Think about that. In 1908, we had no idea it was coming. No telescopes scanning the sky for threats. No computer models tracking orbital mechanics. No planetary defense systems. The first sign that anything was happening was when the sky caught fire over Siberia. Even after Tunguska, the world didn't really wake up to the asteroid threat. It took until 1980, when Luis and Walter Alvarez found that thin layer of iridium in rock layers around the world, iridium being an element that's rare on Earth but common in asteroids, for the scientific community to accept that asteroids could cause mass extinctions. Their proposal that an asteroid killed the dinosaurs was initially ridiculed. Surely, the critics said, something as gradual and subtle as evolution couldn't be disrupted by something as random and violent as a space rock. The debate raged for over a decade until 1990, when the Chicxulub crater was finally confirmed beneath the Yucatan Peninsula. Suddenly, everything changed. The geological record wasn't just a story of slow, gradual change punctuated by occasional volcanic eruptions or ice ages. It was a story of cosmic violence, of random catastrophes that could reset the entire evolutionary clock in a matter of days. Mass extinctions weren't just biological mysteries, they were crime scenes, and the murder weapon was falling from space. This realization led to the Space Guard survey in 1998, the first serious attempt to catalogue potentially dangerous asteroids. The goal was ambitious. Find 90% of near-Earth asteroids larger than 1 kilometer within 10 years. These are the civilization enders, the ones that could cause global catastrophe if they hit. The good news? We've mostly succeeded. We've found over 90% of the big ones, and none of them are on collision courses with Earth. The bad news? There are a lot more smaller asteroids out there, and we've only found a fraction of them. We've spotted about 40% of the 140-meter city killers, asteroids that could devastate a metropolitan area but wouldn't necessarily end civilization. And we've found less than 1% of the 20-meter objects like the one that caused the Tunguska event. That means there are hundreds of thousands of asteroids out there that we haven't detected yet, any one of which could ruin your day if it happened to arrive over your city. This is the cosmic lottery we're all playing, whether we realize it or not. Every day, Earth travels 24 million kilometers through space, threading its way through a solar system full of debris left over from the formation of the planets. Most of that debris is harmless, tiny specks that burn up in our atmosphere as shooting stars. But some of it is larger, more dangerous, and moving in exactly the wrong direction. 2025 DX41 is one of those dangerous pieces of debris. It's been orbiting the Sun peacefully for 4.5 billion years, but now its path intersects with ours at exactly the wrong time. In 14 months, unless we do something about it, our planet is going to find out what it feels like to be hit by 300 meters of space rock moving at 25 kilometers per second. The dinosaurs couldn't do anything about their asteroid. They didn't see it coming, they couldn't calculate its trajectory, and they had no technology to deflect it. They were just passengers on a planet when their number came up in the cosmic lottery. We're different. We saw 2025 DX41 coming 14 months in advance. We know exactly where it's going to hit and when. We have the technology to reach it, to change its course, to make it miss Earth entirely. For the first time in the 4.5 billion year history of impacts in our solar system, the target can fight back. The question is, will that be enough? For most of human history, we were sitting ducks. We looked up at the night sky with wonder. We created myths about the stars and planets. We used celestial navigation to cross oceans and deserts. But we had absolutely no idea that death could fall from above without warning. Think about that for a moment. For 300,000 years of human existence, we've been completely vulnerable to cosmic impacts. Every civilization that ever rose and fell did so under the constant unknown threat of asteroid impact. The Egyptians built their pyramids, the Greeks founded democracy, the Romans conquered the known world, and all of them were one random space rock away from instant extinction. They didn't know it, of course. How could they? When you're worried about finding enough food to survive the winter, or fending off attacks from neighboring tribes, you don't spend much time thinking about the possibility that a mountain-sized chunk of rock might fall out of the sky and end everything. But sometimes, just sometimes, ancient people's got a glimpse of the cosmic shooting gallery we're all living in. Chinese astronomers in 1064 recorded something they called a guest star, a bright object that appeared in daylight and was visible for 23 days. They wrote that it was as bright as Venus and could be seen even when the sun was shining. Modern astronomers think this was probably a near-Earth asteroid reflecting sunlight as it passed close to our planet. The Chinese didn't know what they were looking at, but they were witnessing a cosmic near-miss that could have changed the course of human history. Other ancient records describe dragons or fire serpents streaking across the sky, objects that moved among the stars in ways that didn't match the predictable patterns of planets or comets. We now know these were probably asteroids or meteor showers, but to ancient observers, they were omens, signs from the gods, harbingers of doom or fortune. They were more right than they knew. The systematic search for asteroids didn't begin until New Year's Day, 1801, when Giuseppe Piazzi, an Italian astronomer working at the Palermo Astronomical Observatory, he noticed something unusual. He was conducting a routine survey of star positions when he spotted an object that seemed to move against the background stars from night to night. At first, Piazzi thought he'd discovered a new planet. This was incredibly exciting. Uranus had been discovered just 20 years earlier, and the idea that there might be more planets waiting to be found had astronomers scanning the skies with renewed enthusiasm. Piazzi tracked his mysterious object for 41 nights before losing sight of it, but he'd gathered enough observations to calculate its orbit. What he found was puzzling. The object, Xeris, which he named Ceres after the Roman goddess of agriculture, Xeris, was orbiting the Sun between Mars and Jupiter, exactly where the Titius-Bode law predicted a planet should exist. But it was much smaller than any known planet, and its orbit was slightly different from the perfect circles that planets were supposed to follow. Within a few years, astronomers found 3 more objects in similar orbits: Pallas, Juno, and Vesta. William Herschel, the discoverer of Uranus, coined a new term for these mysterious objects, asteroids, meaning star-like, because they appeared as points of light even in the most powerful telescopes of the time. By 1898, astronomers had found 433 asteroids, all safely contained in what we now call the asteroid belt between Mars and Jupiter. They were interesting scientific curiosities, cosmic collectibles for astronomers to catalogue and study, but they seemed completely irrelevant to life on Earth. They were so far away, so safely contained in their designated region of the solar system. Then came the shock. In 1898, Carl Witt, a German astronomer working at the Berlin Observatory, discovered an asteroid he named Eros. At first, Eros seemed like just another space rock to add to the growing catalogue, but when astronomers calculated its orbit, they realized something disturbing. Eros didn't stay safely in the asteroid belt. Its orbit was elongated, carrying it much closer to the Sun than any previously known asteroid. At its closest approach, Eros came within 22 million kilometers of Earth's orbit. That might sound like a safe distance, and it is, but it shattered the comfortable assumption that asteroids stayed in their assigned region of the solar system. Suddenly, astronomers realized there might be asteroids crossing Earth's orbital path, asteroids that could pose a direct threat to our planet. Eros was the first known near-Earth asteroid, the first member of a population that we now know numbers in the hundreds of thousands. But even after its discovery, the astronomical community didn't immediately grasp the implications. Eros was still millions of Kolbrone, kilometers away at its closest approach. What were the odds that a much larger asteroid might actually hit Earth? The answer came 10 years later, in the most dramatic way possible. On June 30th, 1908, at 7:14 a.m. local time, something exploded above the Podkamennaya Tunguska River in Siberia. We talked about this event in the previous chapter, but think about it from the perspective of early 20th century astronomy. Here was proof that large objects from space could not only reach Earth's atmosphere, but could explode with the force of 1,000 nuclear bombs. The Tunguska event should have been a wake-up call. It should have sparked immediate efforts to scan the skies for potentially dangerous asteroids. Instead, it was largely ignored by the scientific mainstream. Some researchers proposed that it was caused by a small asteroid or comet, but others suggested more exotic explanations: antimatter, mini black holes, even early experiments with Tesla's wireless power transmission. The lack of any recovered meteorite fragments at the Tunguska site made it easy for skeptics to dismiss the asteroid hypothesis. How could an asteroid cause such massive destruction without leaving any physical evidence? It would take decades before scientists understood that small asteroids could explode completely in the atmosphere, leaving nothing but shock waves and scattered dust. More importantly, the Tunguska event happened in one of the most remote regions on Earth. If you wanted to design an asteroid impact that would cause maximum destruction while attracting minimum scientific attention, Siberia in 1908 was perfect. Sparse population, limited communication, and a government more interested in revolution than cosmic catastrophes. So the world went back to sleep, astronomically speaking. Asteroid research continued at a leisurely pace. By 1930, astronomers had discovered over 1,000 asteroids, but they were still viewed as scientific curiosities rather than potential threats. The focus was on understanding the formation of the solar system, not on protecting Earth from cosmic impacts. World War II actually accelerated asteroid research, but not for the reasons you might expect. Military radar systems developed during the war were sensitive enough to detect meteor showers, and radar operators began reporting ghost echoes that didn't correspond to aircraft or ground targets. Investigation of these anomalies led to better understanding of how small meteoroids interact with Earth's atmosphere. But it wasn't until 1980 that the asteroid threat finally received serious scientific attention. That's when Luis Alvarez, a Nobel Prize-winning physicist, and his son Walter, a geologist, published their revolutionary paper proposing that an asteroid impact caused the mass extinction that killed the dinosaurs. The Alvarez hypothesis was based on a thin layer of clay found in rock formations around the world, all dating to exactly 66 million years ago. This clay layer contained unusually high concentrations of iridium, an element that's rare in Earth's crust but common in asteroids and comets. The Alvarezes calculated that a 10-kilometer asteroid could deposit exactly the amount of iridium found in the clay layer. The proposal was initially met with skepticism and often outright hostility from the paleontological community. Dinosaur experts had spent careers developing theories about gradual climate change, volcanic activity, and evolutionary pressures. The idea that a single asteroid impact could cause a mass extinction seemed too random, too catastrophic, too unscientific. But evidence continued to accumulate. In 1990, researchers finally found the smoking gun, the Chicxulub crater buried beneath the Yucatan Peninsula. This massive impact structure, 180 kilometers across, was exactly the right age and size to match the Alvarez hypothesis. Suddenly, everything changed. The geological record wasn't just a story of slow, gradual change. It was punctuated by catastrophic events that could reset the entire evolutionary clock. Mass extinctions weren't just biological mysteries. They were crime scenes with a very specific type of murder weapon. This realization led directly to the modern asteroid detection programs. In 1998, Congress tasked NASA with finding 90% of near-Earth asteroids larger than 1 kilometer in diameter within 10 years. These are the civilization enders, the ones that could cause global catastrophe regardless of where they hit. The SpaceGuard survey, named after a fictional asteroid detection system in an Arthur C. Clarke novel, began operations with a network of ground-based telescopes dedicated to scanning the skies for moving objects. The Catalina Sky Survey in Arizona became the most productive asteroid hunter, discovering about 45% of all known near-Earth asteroids. The Linear program, operated by MIT and the US Air Force, used military tracking technology to spot asteroids. The NEAT program deployed telescopes in Hawaii and California. International partners launched their own detection systems. The Japanese Space Guard Association, the European Space Agency's Space Situational Awareness Program, and dozens of smaller observatories around the world. By 2008, exactly 100 years after Tunguska, the asteroid hunting community had achieved its goal. They'd found over 90% of the kilometer-sized near-Earth asteroids, the ones capable of causing global catastrophe. The good news? None of them are on collision courses with Earth for at least the next century. The bad news? There are a lot more smaller asteroids out there. Today's asteroid detection network is impressive by any measure. The Catalina Sky Survey alone discovers about 2,000 near-Earth asteroids every year. Atlas, with its 4 telescopes in Hawaii and South Africa, scans the entire visible sky every 24 hours, capable of detecting a small asteroid just hours before impact. The NEOWISE Space Telescope, originally designed to study infrared astronomy, has become one of our most effective asteroid hunters by detecting the heat signatures of space rocks. But even with all this technology, we're still playing catch-up. We've found about 40% of the 140-meter asteroids. Yes, the ones that could devastate a major city but wouldn't necessarily end civilization. We found less than 1% of the 20-meter objects like the one that caused the Tunguska event. Think about what that means. There are hundreds of thousands of asteroids out there, each one large enough to flatten a major metropolitan area, and we have no idea where they are or when they might arrive. They're cosmic lottery tickets, and we don't even know how many tickets are in the draw. This is the challenge that the next generation of asteroid detection systems is designed to address. The NEO-Surveyor Space Telescope, launching in 2028, will be the first space-based infrared telescope specifically designed for asteroid hunting. From its position in space, free from atmospheric interference and capable of observing 24 hours a day, NEO-Surveyor should find most of the remaining city-killer asteroids within 5 years of operation. The European Space Agency is developing similar capabilities with their proposed NEOSTEL mission. Ground-based telescopes are getting larger and more sensitive. The Vera Rubin Observatory in Chile will begin operations soon, capable of surveying the entire visible sky every 3 nights with unprecedented sensitivity. But here's the thing about asteroid detection. It's not enough to just find them. You need to find them early enough to do something about it. A 20-meter asteroid detected 6 hours before impact gives you time to evacuate a city, maybe save millions of lives. A 300-meter asteroid detected 14 months before impact gives you time to mount a deflection mission, maybe save civilization itself. This is exactly what happened with 2025 DX41. Maria Gutierrez, working the night shift at Catalina Sky Survey, spotted it exactly when the system was designed to spot it, early enough for humanity to respond. The detection network that began with Giuseppe Piazzi's accidental discovery of Ceres on New Year's Day, 1801, had evolved into a global early warning system, capable of giving us more than a year's notice of incoming threats. But detection is only the first step. Once you know an asteroid is coming, once you've calculated its trajectory and confirmed the impact probability, you face a much more difficult challenge. What do you do about it? For the dinosaurs, that question never arose. They had no warning, no technology, no options. The first sign of trouble was when the sky caught fire above the Yucatan Peninsula, and by then it was far too late. We're different. We have rockets capable of reaching asteroids months or years before they reach Earth. We have nuclear weapons that could vaporize smaller threats. We have the computational power to model complex orbital mechanics and plan precise deflection missions. Most importantly, we have time. 14 months is an eternity in asteroid deflection terms. It's enough time to design, build, and launch multiple spacecraft. It's enough time to gather international cooperation and pool resources from every space agency on Earth. It's enough time to turn humanity's collective technological might toward a single, focused goal, making sure that 2025 DX41 misses our planet entirely. The ancient Chinese astronomers who recorded that guest star in 1064 had no idea they were witnessing a cosmic near-miss. They saw an unusual bright object in the sky and noted it in their records, never knowing that it represented a type of threat that could end human civilization. Today, when Maria Gutierrez spots a moving dot on her computer screen, she knows exactly what she's looking at. She understands the physics, the orbital mechanics, the potential consequences. More importantly, she's part of a global network of observers and analysts who can turn a single observation into a comprehensive threat assessment within hours. We've gone from cosmic ignorance to cosmic awareness in just over 2 centuries. From Giuseppe Piazzi accidentally discovering the first asteroid, to Maria Gutierrez detecting an incoming threat with 14 months warning. From sitting ducks to active participants in our own survival. The question now is whether that's enough, whether 200 years of astronomical progress, combined with 60 years of space technology, is sufficient to deflect a 300-meter asteroid moving at 25 kilometers per second. We're about to find out. Let's go back to that moment when everything changed. It's now 48 hours since Maria Gutierrez first spotted that moving dot, and the confirmation is complete. Every major observatory on Earth has verified the trajectory. The computers have run the calculations thousands of times. The impact probability has actually increased slightly. It's now 97.4%. 2025 DX41 is 300 meters of space rock, moving at 25 kilometers per second, and it will hit Earth in exactly 14 months, 6 days, and 13 hours. The location? Somewhere along a 3,000-kilometer track stretching from the Pacific Ocean through California and Nevada. Best case scenario, it hits water off the coast, creating tsunamis that devastate everything from Alaska to Chile. Worst case scenario, direct impact on Los Angeles, San Francisco, or Las Vegas. And now, the real work begins. Within 24 hours of confirmation, something unprecedented happens. The UN Security Council convenes an emergency session, and for the first time in the organization's history, all 5 permanent members agree unanimously on anything. The resolution is simple. The asteroid threat represents an existential challenge to human civilization and requires the immediate coordinated response of all nations. It passes 15-0. No abstentions, no political grandstanding, no debates about national sovereignty or competing interests. When you're facing extinction, party politics become irrelevant. But here's what's really remarkable about those first few days. The speed. Not just the speed of political response, but the speed of everything. Stock markets crash, then bizarrely recover, as investors realize there's no point in selling if money might not matter in 14 months. The Dow Jones loses 3,000 points in the first hour of trading, then gains 4,000 points by market close, as people decide that if the world's ending, they might as well go out rich. Religious movements surge overnight. Some preach end times. The asteroid is God's judgment, a sign of the apocalypse, proof that humanity has strayed too far from the righteous path. Others organize relief efforts, arguing that if these are humanity's final months, we should spend them helping each other rather than preparing for war. Gun sales spike 5,000% in the United States. Apparently, the prospect of cosmic annihilation makes people want to arm themselves against something. Maybe they're planning to shoot the asteroid. Maybe they're worried about social collapse. Maybe when faced with ultimate helplessness, people just want to feel like they have some control over something, even if it's just the ability to make loud noises and holes in paper targets. Marriage proposals increase by 3,000% worldwide. Nothing says I love you like, let's get married before the world ends. Wedding planners report booking solid through the next 12 months, with many couples specifically requesting outdoor ceremonies under the stars, because apparently irony isn't dead yet. Social media explodes with hashtags #SaveEarth, #Asteroid Impact, #14 months. Bruce Willis jokes flood Twitter for exactly 6 hours before the gravity of the situation silences them. Someone creates a countdown website showing exactly how much time is left until impact, down to the second. It crashes within an hour from traffic overload, gets rebuilt, crashes again, and eventually becomes the most visited website in human history. But between the chaos and the panic and the gallows humor, something extraordinary happens, something that gives me hope about our species. The Planetary Defense Coordination Office, which most people didn't know existed until 3 days ago, suddenly commands resources that would make most government agencies jealous. The PDCO was created in 2016, with a staff of 3 people and a budget that wouldn't cover the catering for a typical government conference. Now it has direct access to the President, unlimited funding authorization, and liaison officers from every major space agency on Earth. Dr. Sarah Martinez, the NASA administrator, finds herself in the surreal position of briefing world leaders on orbital mechanics and deflection strategies. 72 hours ago, she was dealing with budget hearings and congressional testimony about Mars rover missions. Now she's explaining to the President of the United States how to punch an asteroid. The European Space Agency, which had been planning a leisurely comet observation mission scheduled for launch in 2027, suddenly repurposes their half-built spacecraft for asteroid deflection. Engineers work around the clock to modify the probe's trajectory systems and add kinetic impactor capabilities. What was supposed to be a peaceful scientific mission becomes a weapon of planetary defense. SpaceX clears their launch manifest for the next 12 months. Every Falcon Heavy rocket currently in production gets reassigned to asteroid deflection duty. Elon Musk, in a rare display of restraint, limits himself to just 3 tweets about the situation, all of them surprisingly helpful, and none of them mentioning Dogecoin or flamethrowers. Blue Origin offers their New Glenn rockets, still in testing but capable of heavy lift. Jeff Bezos quietly offers his entire fortune, $180 billion, to fund additional deflection missions. When asked why, he simply says, "What's the point of being the richest man on Earth if there's no Earth?" The Chinese National Space Administration, normally secretive about their capabilities, opens their facilities to international inspection and offers their Long March rockets for the deflection effort. They also reveal ion drive technology that's apparently years ahead of anything the West thought they had. Suddenly, international space competition becomes international space cooperation. India's space program, famous for launching missions on shoestring budgets, offers their precision manufacturing capabilities and mission control expertise. The Japanese contribute their asteroid sample return technology. They've already successfully visited asteroids Itokawa and Ryugu, and they understand better than anyone how to navigate in the vicinity of small space rocks. Even North Korea, which has spent decades using missile technology to threaten its neighbors, quietly offers their launch capabilities for planetary defense. Kim Jong-un, in a statement that surprises everyone, says, "The Democratic People's Republic of Korea will defend Earth against all cosmic threats, regardless of their ideology." It's the first time anyone can remember North Korean propaganda actually making sense. Within 1 week, 7 days, humanity has assembled the largest space mission in history. Not just the largest by one country or one agency, but the largest collaborative effort in the history of space exploration. The Apollo program that put 12 men on the moon involved about 400,000 people. The International Space Station required cooperation between 5 space agencies. This mission involves every space agency on Earth, plus dozens of commercial companies, plus research institutions in 47 countries. The plan that emerges is elegant in its simplicity and terrifying in its complexity. 8 kinetic impactors, launched over 6 weeks, designed to hit the asteroid from multiple angles and nudge it just enough to miss Earth. Each impactor weighs about 1,000 kilograms and carries no explosives, just mass and velocity, converted into momentum at the moment of impact. The physics is straightforward. At 14 months out, we need to change the asteroid's velocity by just 2 centimeters per second, roughly the speed of a crawling snail. That tiny change, applied early enough, will cause the asteroid to arrive at the intersection point with Earth's orbit about 4 hours early or late. Since Earth travels at 30 kilometers per second, 4 hours means the asteroid will miss us by about 400,000 kilometers, farther than the distance to the Moon. Wait until 3 months before impact, and we'd need to achieve 100 times that velocity change. Wait until 1 month before impact, and we'd need to move the asteroid at several meters per second, 280, essentially impossible with current technology. This is why early detection isn't just important, it's everything. Maria Gutierrez didn't just spot an incoming asteroid, She spotted it early enough for us to do something about it. The launch schedule is punishing. Impactor 1 launches from Kennedy Space Center in 3 weeks, targeting an intercept 4 months before the asteroid reaches Earth. Impactor 2 launches from French Guiana 2 days later on a decilose, slightly different trajectory. Impactors 3 and 4 launch from China's Wenchang Space Center, 5 and 6 from Russia's Baikonur Cosmodrome, 7 from India's Sriharikota, 8 from Japan's Tanegashima Space Center. Each launch window is calculated to the minute. Miss your window, and you have to wait for the next orbital alignment, which might not come in time. The margin for error is essentially 0. But here's what gives me chills about this whole operation. The cargo. Impactor 1 carries more than just guidance systems and communication equipment. In a specially designed compartment, it carries 8 billion handwritten names collected in just 2 weeks, through a global website where people could submit their signatures for inclusion on humanity's first punch back at the cosmos. 8 billion names. Every person on Earth who wanted their signature on this mission could include it. Children drew pictures of Earth with hearts around it. Adults wrote messages like, "Not today," "Universe," and "Earth fights back." Scientists included equations. Artists included sketches. Poets included verses about survival and defiance and hope. The Chinese impactor includes ancient poems about shooting down suns, verses written 2,000 years ago by people who could never have imagined their words traveling through space to deflect an asteroid. The Indian mission carries recordings of every language spoken on Earth, over 7,000 languages, including some spoken by only a few dozen people in remote villages who wanted their voices included in humanity's cosmic statement. The Russian impactor carries soil samples from every continent, including a vial of sand from every major city that could be affected by the impact. The European mission includes seeds from endangered plants, DNA samples from threatened species, and cultural artifacts representing the diversity of human civilization. Even the North Korean impactor carries something symbolic, a peace treaty signed by Kim Jong-un and South Korean President, officially ending the Korean War 64 years after the armistice. Apparently, the prospect of extinction makes old grudges seem petty. This isn't just a deflection mission, it's a statement. 8 spacecraft, launched by 8 different countries, carrying the signatures, voices, hopes and dreams of 8 billion people. If 2025 DX41 represents cosmic indifference to human survival, then these impactors represent human refusal to accept that indifference. The launches begin on schedule. Impactor 1 lifts off from Kennedy Space Center at 6:37 a.m. Eastern Time on a Tuesday morning that feels like the most important Tuesday in human history. The Falcon Heavy rocket performs flawlessly, carrying its precious cargo away from Earth at 11 kilometers per second, beginning a 6-month journey to intercept an asteroid that most people had never heard of until 3 weeks ago. The world watches. Not just space enthusiasts or science fans. Everyone. The launch gets higher television ratings than the Super Bowl, the World Cup final, and the Olympics combined. Schools cancel classes so students can watch. Businesses close so employees can gather around televisions. Times Square, Piccadilly Circus, Red Square. Every major public space on Earth fills with people staring at giant screens, showing a rocket carrying humanity's hopes into the void. When the rocket disappears into the sky and Mission Control confirms successful orbit insertion, 8 billion people cheer simultaneously. It's probably the loudest sound humans have ever made as a species. 2 days later, Impactor 2 launches from French Guiana. Same flawless performance, same global celebration. 4 days after that, Impactors 3 and 4 launch from China in a spectacular dual launch that puts both spacecraft on slightly different trajectories toward the same target. By the end of 6 weeks, all 8 impactors are in space, following carefully calculated paths that will converge on 2025 DX41, like arrows shot by the best archers in human history. If the best archers in human history were rocket scientists with unlimited budgets and the survival of civilization depending on their accuracy. The travel time varies for each impactor. Some take direct routes. Others use gravitational assists from Venus or Mars to increase their velocity at impact. The first impact is scheduled for 6 months after launch. The last impact will occur just 2 weeks before the asteroid would have hit Earth. During those 6 months, something remarkable happens to human civilization. Knowing that our survival depends on the success of these 8 missions creates a sense of unity that transcends every political, cultural, and religious boundary that has ever divided us. Climate change activists and fossil fuel executives work together on emergency evacuation plans for the West Coast. Democrats and Republicans in Congress pass asteroid defense funding bills by unanimous votes. The European Union and the United Kingdom resolve their post-Brexit trade disputes in a single afternoon because, as one negotiator puts it, what's the point of arguing about customs regulations if there might not be any customs to regulate? China and Taiwan jointly develop impact modeling software. Israel and Palestine collaborate on tsunami warning systems. India and Pakistan share satellite tracking data. Russia and Ukraine, well, they're still fighting, but they've agreed to a temporary ceasefire for asteroid tracking purposes. Environmental groups that have spent decades opposing space exploration suddenly become its biggest advocates. Save the Whales transforms into Save the Planet overnight. Protesters who once chained themselves to rocket launch facilities now organize fundraisers for additional deflection missions. The global economy reorganizes itself around Asteroid. Impact preparation. Tourism to the potential impact zone plummets to zero. Insurance companies stop selling policies for anything on the West Coast. Real estate prices in California crash, while property values in places like Nebraska and Montana skyrocket as people realize that being far from the ocean might be advantageous if this deflection mission fails. But something else happens too. Innovation explodes. Faced with the possibility that these 8 impactors might not be enough, engineers around the world begin developing backup plans. Solar sail concepts that could use light pressure to nudge the asteroid. Nuclear pulse propulsion systems that could deliver much larger velocity changes. Even more exotic ideas like lasers powerful enough to vaporize asteroid material and create thrust through outgassing. Universities establish emergency asteroid deflection research programs. High school students win science fairs with models of kinetic impactors. Children's toy companies start selling Save Earth space mission playsets. Hollywood puts every superhero movie on hold and starts producing documentaries about asteroid science. The asteroid hunting programs expand dramatically. If we can't deflect 2025 DX41, we at least want to make sure we never get surprised like this again. The budget for the Planetary Defense Coordination Office increases by 10,000% overnight. Countries that have never had space programs suddenly announce plans for asteroid detection satellites. 6 months after launch, the impacts begin. Impactor 1 reaches 2025 DX41 on schedule at precisely 11:43 a.m. Greenwich Mean Time on a Thursday that becomes known as Punch Day. The spacecraft, traveling at 6 kilometers per second relative to the asteroid, slams into the space rock with the force of several tons of TNT. Every telescope on and off Earth is watching. The impact creates a brilliant flash, visible from 400 million kilometers away. More importantly, it creates a plume of debris that acts like a rocket engine, amplifying the momentum change by a factor of 3. Trajectory analysis begins immediately. Within 6 hours, the results are confirmed. Impactor 1 has changed the asteroid's velocity by 0.8 centimeters per second. It's working. 4 days later, Impactor 2 hits from a different angle. Another successful impact, another velocity change. The asteroid is starting to drift away from its collision course with Earth, slowly but measurably. By the fifth impact, trajectory analysis shows a 70% chance that the asteroid will miss Earth. By the sixth impact, the probability of a miss increases to 85%. By the seventh impact, it's 92%. The eighth and final impact occurs just 14 days before the asteroid would have hit Earth. The spacecraft, moving faster than any of the previous impactors due to a gravitational assist from Mars, delivers the largest velocity change yet. The impact is so violent that debris from the asteroid becomes visible to amateur astronomers on Earth. Final trajectory analysis takes 18 hours. Computers around the world run calculations continuously, checking and double-checking the orbital mechanics. At exactly 6 p.m. Eastern Time on a Sunday evening, Dr. Sarah Martinez steps up to a podium at NASA headquarters to announce the results. "Ladies and gentlemen," she says, and her voice carries to 8 billion people watching on television, listening on radio, streaming on their phones. 2025 DX41 will pass Earth at a distance of 42,300 kilometers. The asteroid will miss our planet by approximately 1/10 the distance to the Moon. The silence lasts exactly 2 seconds. Then 8 billion people cheer simultaneously for the second time in 14 months, and this time the sound is even louder. We won, barely, by cosmic standards. 42,000 kilometers is still uncomfortably close, closer than many of our communication satellites, but it's far enough. The asteroid will pass by like a cosmic near miss, close enough to study but too far away to hurt anyone. Humanity has faced extinction and punched back. We looked up at the night sky, saw death falling toward us, and said, "Not today." The celebration lasts exactly 1 week. Then the real work begins. Now, let me tell you about the science behind saving the world. Because when you're trying to deflect a 300-meter asteroid moving at 25 kilometers per second, the physics are both elegantly simple and maddeningly complex. Here's the elegant part. We don't need to destroy the asteroid. We don't need to vaporize it or blow it into tiny pieces or fundamentally alter its composition. We just need to change its arrival time at the intersection point with Earth's orbit by a few hours. Think of it like this. Imagine you're driving to an intersection, and there's another car approaching the same intersection from a different direction. Both of you are going to arrive at exactly the same time, which means collision. But if you can make the other car arrive just a few minutes early or late, you'll both pass through the intersection safely, never getting closer than the width of the intersection itself. That's exactly what we need to do with 2025 DX41. The asteroid and Earth are both heading toward the same point in space, is one of their orbits, and they're scheduled to arrive at exactly the same time. We need to make the asteroid arrive a few hours early or late, and Earth will sail through the intersection point with the asteroid safely ahead of or behind us. At 14 months out, we need to change the asteroid's velocity by just 2 centimeters per second. 2 centimeters per second. That's roughly the speed of a crawling snail. If you've ever watched a snail move across a sidewalk, that tiny, barely perceptible motion is all the velocity change we need to save civilization. But here's the maddeningly complex part. Delivering that tiny velocity change to a 300-meter chunk of rock floating 400 million kilometers away requires hitting it with spacecraft, moving at 6 kilometers per second, with precision measured in meters. It's like throwing a baseball from New York and hitting a specific window in Los Angeles, except both the baseball and the window are moving at incredible speeds in 3-dimensional space. The physics underlying asteroid deflection were actually proven just 2 years ago, in 2022, when NASA's DART mission, ISTO Double Asteroid Redirection Test, 2 deliberately crashed into an asteroid moon called Dimorphos. DART was about the size of a washing machine, and it hit Dimorphos at 6.14 kilometers per second. The results exceeded all expectations. Instead of changing Dimorphos's orbital period by the predicted 73 seconds, the impact changed it by 33 minutes, HS, almost 30 times more than anticipated. The secret was something called momentum enhancement. The impact created a massive plume of debris that acted like a rocket engine, amplifying the momentum change far beyond what the spacecraft itself could deliver. Picture this. When DART hit Dimorphos, it didn't just transfer its own momentum to the asteroid. The impact excavated thousands of tons of rock and dust, blasting it away from the asteroid at high speed. By Newton's third law, time, for every action there's an equal and opposite reaction. All that material flying away from the asteroid pushed the asteroid in the opposite direction. It was like the difference between gently pushing a bowling ball versus hitting it with a sledgehammer that causes it to crack and spray fragments everywhere. Both deliver momentum to the ball, but the sledgehammer creates secondary effects that amplify the momentum change dramatically. This is exactly what we're counting on with 2025 DX-41. Each of our 8 impactors will hit the asteroid and create its own debris plume, its own mini rocket engine, its own momentum amplification. The key is hitting from multiple angles so that the momentum changes add up rather than cancel each other out. The mission design is like a cosmic billiards shot calculated by the best physics minds on Earth. Impactor 1 hits the asteroid on its leading edge, the direction it's traveling in its orbit around the Sun. This slows the asteroid down slightly, causing it to arrive at Earth's orbit a little bit late. Impactor 2 hits from a different angle, adding a slight sideways component to the velocity change. By the time all 8 impacts are complete, the asteroid's velocity vector will have changed in both magnitude and direction. It will be moving slightly slower and in a slightly different direction, which means it will arrive at the intersection point with Earth's orbit several hours after Earth has already passed through. But executing this plan requires navigation precision that pushes the limits of current technology. Each impactor must travel for months through the vacuum of space, making tiny course corrections along the way, and arrive at exactly the right place at exactly the right time to hit a target that's only 300 meters across. To put that in perspective, imagine throwing a dart at a dartboard from across a football field. But the dartboard is moving at 25 kilometers per second, and you have to throw the dart from a platform that's also moving at 30 kilometers per second, and you get only one throw. Oh, and if you miss, everyone dies. No pressure at all. The navigation challenges are solved using a combination of technologies that didn't exist 20 years ago. Each impactor carries a sophisticated autonomous navigation system that can track the asteroid using optical cameras and adjust its trajectory in real time during the final approach. The spacecraft can literally see the asteroid growing larger as they approach and make last-minute corrections to ensure a direct hit. But even before the final approach begins, each impactor follows a precisely calculated trajectory that takes advantage of gravitational assists from other planets. Impactor 3, for example, swings by Venus to increase its velocity, then uses Earth's gravity for a final speed boost before heading toward the asteroid. The result is an impact velocity of over 8 kilometers per second, TFA, fast enough to travel from Los Angeles to New York in under 8 minutes. The spacecraft themselves are marvels of engineering efficiency. Each one weighs about 1,000 kilograms, A1Z, roughly the size of a small car, but most of that mass is fuel and propulsion systems needed for the journey to the asteroid. The actual impactor part, the chunk of metal that delivers the kinetic energy, weighs only about 200 kilograms. You might think we'd want to make the impactors as heavy as possible to deliver maximum momentum, but there's a trade-off. Heavier spacecraft require bigger rockets and more fuel, which means higher costs and longer development times. The DART mission proved that relatively small impactors can achieve large momentum changes through debris enhancement, so we optimized for accuracy and reliability rather than raw mass. Each impactor carries no explosives. This isn't a Hollywood movie where we send Bruce Willis to plant nuclear bombs inside the asteroid. The impactors are purely kinetic weapons. Mine. They deliver energy through mass times, velocity squared, converting their motion into momentum change at the moment of impact. This approach has several advantages. First, it's simple and reliable. Kinetic impactors have no complex mechanisms that could fail at the crucial moment. Second, it's predictable. We can calculate exactly how much momentum will be transferred based on the impactor's mass and velocity. Third, it's testable. The DART mission already proved the concept works. The timing of the impacts is carefully orchestrated to maximize the cumulative effect. The first impact occurs 6 months before the asteroid would hit Earth, when small velocity changes produce large trajectory changes. Each subsequent impact occurs closer to Earth encounter, but by then the asteroid is already moving away from its collision course. The debris plumes created by the impacts are visible from Earth through large telescopes, allowing astronomers to confirm that each impact occurred successfully and measure the resulting velocity change. It's like having 8 chances to fine-tune the asteroid's trajectory, with each impact providing feedback for the next one. The international cooperation required for this mission is unprecedented in the history of space exploration. Each impactor is built by a different country or space agency, but they all must work together as a coordinated system. The navigation software is shared between all spacecraft, so they can avoid colliding with each other during the approach to the asteroid. Communication protocols are standardized so that mission control centers in 8 different countries can coordinate the impacts. Launch schedules are synchronized to ensure that all spacecraft arrive at the asteroid within the optimal time window. It's like conducting a symphony orchestra where the musicians are scattered across 8 countries and the performance takes 6 months to complete. The backup plans are equally impressive. If any impactor fails to reach the asteroid, the remaining spacecraft can compensate by adjusting their impact points and velocities. Computer simulations show that the mission can succeed even if 2 or 3 impactors fail completely, though the margin for error decreases with each failure. If the entire kinetic impactor approach fails, there are contingency plans involving nuclear explosive devices that could vaporize part of the asteroid and create a much larger momentum change. But this nuclear option, pun intended, comes with significant risks and unknowns, so it's reserved as a last resort. The beauty of the kinetic impactor approach is its simplicity and scalability. If we had detected 2025 DX41 even earlier, say 5 years before impact, we could have deflected it with a single small spacecraft. If we had detected it later, say 6 months before impact, Slex as Ma, we would have needed much larger impactors or exotic technologies like nuclear explosives. The 14-month warning provided by Maria Gutierrez's discovery hits the sweet spot where kinetic deflection is both feasible and reliable. It's enough time to design, build, and launch multiple spacecraft, but not so much time that political support and funding disappear due to the distant nature of the threat. This is why the asteroid detection programs are so crucial. Every month of advance warning exponentially increases our deflection options and decreases the resources required. A threat detected 5 years early can be deflected with technology we already have. A threat detected 5 months early requires heroic engineering efforts and massive international cooperation. A threat detected 5 weeks early, well, that's when we start talking about evacuation rather than deflection. The DART mission in 2022 was humanity's first planetary defense test, but it was conducted against an asteroid that posed no threat to Earth. The deflection of 2025 DX41 is our first operational planetary defense mission, the first time we've deliberately changed the trajectory of an asteroid that was actually going to hit us. The psychological impact of this success cannot be overstated. For the first time in the 4.5 billion year history of life on Earth, a species has the ability to prevent its own, extinction by cosmic impact. We're no longer passengers on a planet, helplessly waiting for the next asteroid to end our story. We're active participants in our own survival. The technology developed for asteroid deflection has applications far beyond planetary defense. The same navigation systems that guide impactors to asteroids can guide spacecraft to Mars with unprecedented precision. The same propulsion systems that accelerate impactors to high velocities can power fast missions to the outer planets. The same international cooperation frameworks that made the deflection mission possible can support future Mars exploration, lunar bases, and asteroid mining operations. In a very real sense, the threat posed by 2025 DX-41 has accelerated human space capabilities by decades. Technologies that would have taken 20 or 30 years to develop under normal circumstances were perfected in 20 months under the pressure of species survival. But perhaps the most remarkable aspect of the entire deflection mission is how routine it makes the impossible seem. Hitting an asteroid with 8 spacecraft launched from 8 different countries sounds like science fiction, but the engineering is fundamentally an extension of technologies we already had. We've been sending spacecraft to other planets for 50 years. We've been conducting precision rendezvous and docking operations since the Gemini program. We've been using gravitational assists for interplanetary missions since the 1970s. What's new is the integration of all these capabilities into a single, coordinated mission with the highest possible stakes. It's like taking every skill humans have developed in 60 years of space exploration and applying them all to one crucial problem: making sure a particular chunk of rock misses Earth by a comfortable margin. The fact that we succeeded, that all 8 impactors hit their target and delivered the precise velocity changes needed to deflect 2025 DX-41, proves something important about human technological capability. When we're truly motivated, when survival is at stake, when political and cultural differences are set aside in favor of species preservation, we can accomplish almost anything. The dinosaurs had no technology to save themselves when their asteroid arrived 66 million years ago. They were simply passengers on a planet when the cosmic lottery came up against them. We're different. We have rockets and computers, and international cooperation, and most importantly, the knowledge that we can fight back against cosmic threats. 2025 DX-41 was our first test of planetary defense under real conditions, and we passed with flying colors. The asteroid will sail harmlessly past Earth at a distance of 42,000 kilometers, close enough to study with telescopes, but far enough away to pose no threat to anyone. We looked extinction in the eye and said, "Not today." And that changes everything about humanity's relationship with the cosmos. The asteroid passes Earth at 42,300 kilometers, 200 kilometers, closer than many of our communication satellites, but far enough to pose no threat. For exactly 7 days, the entire planet celebrates. Governments declare holidays, cities organize parades, families reunite to watch the asteroid's closest approach through telescopes and binoculars. This cosmic visitor that almost ended everything but instead became a symbol of human ingenuity and cooperation. Then, reality sets in. The celebration ends not with a bang but with a question: what now? For 14 months, humanity had a single, unifying purpose. Every decision, every priority, every resource allocation was filtered through one simple criterion: will this help us deflect the asteroid? Political differences were set aside. International rivalries were forgotten. Economic systems reorganized themselves around species survival. Now, suddenly, that organizing principle is gone. We saved the world, and everybody wants to know what we're going to do for an encore. The answer, it turns out, is everything. The near miss with 2025 DX-41 catalyzes changes that reshape human civilization in ways no one anticipated. It's not just that we developed new technologies or improved international cooperation, though we did both of those things. It's that the experience of facing extinction and successfully fighting back fundamentally alters how our species thinks about itself and its place in the universe. Within 6 months of the asteroid's closest approach, the United Nations undergoes the most significant restructuring in its 78-year history. The Security Council expands from 15 members to 25, adding permanent seats for space-capable nations that contributed to the deflection mission. But more importantly, the UN establishes its first truly global authority with actual power, the Planetary Defense Council. The PDC is unlike any international organization that has ever existed. It's funded by a mandatory 0.1% tax on all military budgets worldwide, ATE, a cosmic insurance premium that generates over $20 billion annually. Its mandate is simple: ensure that humanity never again faces extinction from a cosmic impact without adequate warning and response capability. The PDC has the authority to commandeer any launch vehicle, satellite, or space facility on Earth for planetary defense purposes. It can override national sovereignty when species survival is at stake. Most remarkably, every nation on Earth signs the Planetary Defense Treaty without reservation, because the alternative, facing the next asteroid threat with the same 14-month scramble we just endured, is unthinkable. The asteroid mining industry, which had been struggling to achieve economic viability for decades, suddenly becomes the hottest investment sector on the spore. Earth. The same deflection technologies that saved us from 2025 DX-41 can be used to capture and redirect resource-rich asteroids toward Earth orbit. That $30 trillion metallic asteroid Psyche, which we talked about earlier, it's now within reach using proven asteroid deflection technology. Within 2 years of the near miss, the first commercial asteroid capture mission launches, targeting a small metallic asteroid for delivery to lunar orbit. The mission succeeds beyond all expectations, delivering enough platinum, gold, and rare earth elements to supply Earth's industrial needs for decades. Scarcity, at least for certain materials, begins to become an obsolete concept. The psychological transformation is even more profound than the technological advancement. Children who live through the 14-month countdown grow up with a fundamentally different worldview than any previous generation in human history. They understand, in a way that no humans ever have before, that Earth isn't separate from space but part of it. They know that our planet orbits through a cosmic shooting gallery, and they've seen firsthand that we can defend ourselves. These children become adults who look at space not as a distant frontier, but as humanity's natural environment. They support space exploration not because it's scientifically interesting, but because it's existentially necessary. They understand that becoming a spacefaring species isn't about adventure or discovery, it's about survival. Environmental movements gain unprecedented momentum, powered by a simple, irrefutable argument: we just spent trillions of dollars and mobilized the entire planet to save Earth from a space rock. Shouldn't we protect it from ourselves? Climate change activism, biodiversity conservation, and pollution reduction efforts receive support from people who might have been skeptical before witnessing humanity's coordinated response to the asteroid threat. If we can work together to deflect an asteroid, activists argue, we can certainly work together to reduce carbon emissions. If we can mobilize global resources to save the planet from cosmic impact, we can mobilize similar resources to save it from ecological collapse. The space industry expands exponentially. Launch costs, driven down by massive government investment and international competition during the deflection mission, continue falling as demand increases. What cost $10,000 per kilogram to launch before the asteroid crisis now costs less than $100 per kilogram. Space becomes accessible not just to government agencies, but to universities, companies, and eventually individuals. Mars missions, which had been distant dreams requiring decades of planning and international negotiation, become routine operations using technology developed for asteroid deflection. The same ion drives and nuclear propulsion systems that powered our impactors make the journey to Mars faster and cheaper than anyone thought possible. The first permanent Mars colony, established just 5 years after the asteroid deflection, is populated largely by people who want to ensure that human civilization exists on multiple worlds in case Earth faces another cosmic threat. The Moon becomes humanity's first true space settlement, not because of scientific interest or national prestige, but because it's the ideal location for asteroid detection and deflection systems. Lunar-based telescopes, free from atmospheric interference and capable of operating continuously, provide complete sky coverage for asteroid detection. Lunar manufacturing facilities produce deflection spacecraft using materials mined from asteroid captures. But perhaps the most significant change is psychological. For 4.5 billion years, life on Earth has been subject to periodic cosmic catastrophes beyond its control. Mass extinctions weren't just biological phenomena, they were cosmic events that reset the evolutionary clock whenever the universe decided to throw rocks at our planet. We've broken that cycle. The generation that lived through the asteroid deflection looks up at the night sky with a fundamentally different perspective than any humans in history. Previous generations saw the stars as distant, unreachable points of light, beautiful but irrelevant to daily life. We see the stars as a neighborhood we're learning to navigate and protect ourselves within. Previous generations feared cosmic threats because they were powerless to respond to them. We've proven that we're not powerless. We have telescopes to see threats coming, rockets to reach them, and the international cooperation necessary to mount an effective response. We're no longer waiting for the next impact. We're ready for it. The Tunguska event in 1908 flattened 2,000 square kilometers of Siberian forest, and humanity didn't even understand what had happened until decades later. The Chelyabinsk meteor in 2013 injured over 1,000 people, and we had less than a day's warning. 2025 DX 41 could have devastated the entire west coast of North America, but we deflected it with 14 months to spare. The trend is clear. We're getting better at this. Each cosmic threat teaches us more about detection, trajectory calculation, and deflection techniques. The Planetary Defense Council maintains detailed plans for responding to threats of every size, from 20-meter city killers to 10-kilometer civilization enders. We're not just reacting to cosmic threats anymore, we're preparing for them. The asteroid belt, once viewed as a distant curiosity, becomes humanity's new frontier. Mining operations extract water for fuel and metals for construction. Scientific stations study the formation of the solar system using pristine samples that have been preserved in the deep freeze of space for 4.5 billion years. Tourist destinations offer once-in-a-lifetime opportunities to experience zero gravity and see Earth from space. Most remarkably, the same gravitational dynamics that created the asteroid threat in the first place become tools for human expansion throughout the solar system. Jupiter's massive gravity, which prevented the formation of a planet between Mars and itself and created the asteroid belt, now provides gravitational assists for spacecraft traveling to the outer solar system. The cosmic forces that threaten to destroy us become the highways we use to explore and settle the solar system. 20 years after the deflection mission, humanity has permanent settlements on the Moon, Mars, and several asteroids. The population of space grows from a few hundred astronauts to tens of thousands of permanent residents. Children are born and raised in space, becoming the first generation of humans who think of multiple worlds as home. The asteroid detection network expands far beyond Earth. Space-based telescopes positioned throughout the solar system provide complete coverage of potential threats decades before they could pose any danger. Automated deflection systems, deployed in advance near likely asteroid trajectories, can respond to threats without requiring new missions from Earth. But the most profound change isn't technological, it's philosophical. Humanity's successful deflection of 2025 DX41 marks the transition from a species confined to a single planet to a species capable of controlling its cosmic environment. We're no longer subject to the random violence of the universe. We're participants in cosmic evolution, actively shaping the solar system to serve human needs and ensure human survival. The dinosaurs ruled Earth for 165 million years, but they were passengers on a planet, subject to cosmic forces beyond their understanding or control. When their asteroid arrived, they had no warning, no technology, no options. They were simply wiped out by a universe that didn't care about their fate. We've evolved beyond that vulnerability. We're not passengers on Earth anymore. We're the crew. We monitor our cosmic environment. We respond to threats. We've taken active control of our survival as a species. The universe is still vast and dangerous, but we're no longer helpless within it. Maria Gutierrez, the graduate student whose sharp eyes first spotted 2025 DX41 moving against the star field, becomes the most famous astronomer in human history. Universities name departments after her. Asteroid detection systems are called Maria telescopes. Children learn her name alongside Galileo and Einstein as one of the people who fundamentally changed humanity's relationship with the cosmos. But when asked about her role in saving the world, she always deflects the credit. "I just did my job," she says. "I was trained to look for moving dots, and I found one. The real heroes are the 8 billion people who decided to work together instead of giving up." She's right, of course. The detection was just the beginning. The deflection required the coordinated effort of every space agency on Earth, the cooperation of countries that had been enemies for decades, and the support of a global population that suddenly understood that human survival depends on our ability to work together against cosmic threats. The asteroid that almost ended human civilization instead became the catalyst for humanity's emergence as a spacefaring species. 2025 DX41, the 300-meter chunk of rock that could have devastated the West Coast, passed harmlessly by at 42,000 kilometers and continued on its ancient orbit around the Sun, completely unaware that it had just triggered the greatest transformation in human history. Today, as I finish telling you this story, the descendants of those 8 impactor spacecraft continue their journey through the solar system. Their missions complete, they've become humanity's first permanent ambassadors to deep space, carrying 8 billion signatures and the hopes of an entire species as they travel toward the stars. Their messages in bottles, thrown into the cosmic ocean by a species that faced extinction and chose to fight back. If any alien civilization ever finds them, they'll know that Earth was once home to a species intelligent enough to detect cosmic threats, brave enough to face them, and wise enough to work together when survival was at stake. They'll know that when the universe tried to end our story, we wrote a different ending, and that changes everything about what it means to be human in a universe full of rocks moving at 25 kilometers per second. We're no longer afraid of the dark. We've learned to punch back. Thank you for joining me on this journey through humanity's closest call and greatest triumph. Whether you're relaxing at home, finishing your commute, or settling in for the evening, I hope this story reminds you that we're capable of incredible things when we work together toward a common goal. The next time you look up at the night sky, remember, we're not just observers of the cosmos anymore, we're participants, and that makes all the difference.